Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about rotational kinetic energy. So let us begin by sort of reviewing or recalling a few things that we've covered in previous videos. This video, of course, is a continuation of my discussion of rotational dynamics. So what all do we need to recall? I guess we could recall the work and kinetic energy theorem if we wanted to. So work is equal to change in kinetic energy for a system. That was the work and kinetic energy theorem. And that, of course, we used it before in translational motion to discuss translational kinetic energy as being changed by work. And translational kinetic energy, we'll say K sub T for trans, or maybe K translational. This was the kinetic energy of an object which is moving from one point to another. KT is 1/2 mv squared. Beyond this, we might also recall the conditions for rotational motion. So we have rotational motion, and the main things that we want to include here would be the relationship omega equals v over r, or in other words, v is omega r. This v is the tangential speed, so I'm going to use a lowercase t to distinguish it from the uppercase T, translational. Of course, the center of mass speed for a system that's rolling without slipping ends up also looking like omega times r. And then beyond this, maybe how do we define work? So work is defined as force dotted with displacement, and so this is Fx delta x, Fy delta y, and those two added to Fz delta z. And maybe we could also define, just for the fun of it, torque, which is R cross F. So it's quite a few things that are kind of built up in the back of our minds to discuss this. So where are we going with all this? Let's consider an object, maybe a wheel, for example. Maybe like a millstone would be a better example. So millstone basically just spins in place without rolling anywhere or translating anywhere. So this thing is basically just kind of spinning about its axis. It's not rolling, but it is spinning. Now let's consider a piece of this millstone, maybe this piece right here. Okay, so this piece right here at this time has a motion which is tangential in nature. So we have some velocity vectors, and notice that the inner part of it has a slightly lower tangential velocity than the outer part because the radii would be different to them. So if you reduce this to a point mass that everything has the same tangential velocity, then we would use the radius r, and we could say that the v for this little bit of it is r times omega. All right, so far so good. Now what's the kinetic energy of this little piece of mass? Well, if we consider this to be translating, albeit translating and then translating and then translating and translating, or translate, 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 basically making a small translation and then change a direction, then our kinetic energy, kT, or we'll just simply say K in a moment, should look like 1/2 of the mass of this little piece times the tangential speed of the little piece. And so that's 1/2 of whatever the piece's mass is times r squared omega squared. Now, if I redraw this, and instead of imagining it to be an entire wheel spinning about a given point, if I just imagine this to be like uniform circular motion of this dot moving around the axis of the wheel, then what I've just found here, if this is Vt, if this is r, and if this rate of revolution is omega, what I've just found is that the translational kinetic energy for this one piece, 1/2 m r squared omega squared, I noticed that for a point mass, this right here would have a moment of inertia of mr squared about this point right here. So we could kind of go back here to the stuff that we're recalling and recall that the moment of inertia is mr squared, and that is for a point mass. All right, so this kinetic energy suddenly looks like 1/2 I omega squared. Okay, and I've dropped the t because at this point I've gone from having a translational looking kinetic energy in terms of Vt. K translation should look like 1/2 mvt squared, or mv squared. I've gone from terms of mv squared to terms of I omega squared. And so properly speaking, this is more like a rotational kinetic energy. Now the other thing is that I've defined this as I omega squared. That means that I can go back to my original wheel. Remember that my original wheel consists of many of these little point masses, and I could pick any given point mass and do the same thing, and I'd find that that point mass again has a kinetic energy of 1/2 I omega squared. And so if I add up all the little points of mass on this wheel that are moving, then the whole thing collectively, and I'm just going to kind of like shade the whole thing except for this little cutout area that's the axle, this whole thing has moment of inertia big I, and it's moving at omega. My rotational kinetic energy for the whole wheel remains 1/2 I omega squared. And so now I have sort of a boxable equation. I've now got an equation for rotational kinetic energy. I've got an equation for translational kinetic energy. And so now let's take this one step further and say, what if I have an object that is rolling without slipping? And this could be a wheel, it could be a can of soup, it could be a ball. Any of those things have a definable moment of inertia. So this thing is rolling omega, here's r, and the whole thing has a center of mass motion, v center of mass. My total kinetic energy, K total, should be KT plus KR. But that means that the total kinetic energy for this is 1/2 mv center of mass squared plus 1/2 I omega squared. And we can kind of box that result as like the overall result, but we can also remember that v center of mass is equal to omega r, and so you can kind of combine this whole thing to look like K total is equal to 1/2 of basically mr squared plus I times omega squared. So that's putting everything in terms of just omega. You could also, in principle, put everything in terms of just r, of just a v, by dividing everything by an r, or by, excuse me, multiplying the omega term by r and dividing the I by an r squared term. So you could also write k total is equal to 1/2 times m plus I over r squared times v center of mass squared. That's also valid. All right, so that is rotational kinetic energy for us. Today's video, I just want to do a relatively short example of this to close. All right, so I've decided to give us an example here that has two parts. So maybe it's not the simplest possible example, but it's a good example that has work kinetic energy in it, but also that explicitly calculates the energy for rotation and for translation. Because without that explicit statement, we could always just do the thing symbolically and then never actually calculate rotational kinetic energy, of which I also wanted some example. So this is kind of like a twofer. So how much work must be done to accelerate a solid disk from rest to a center of mass speed of 4 meters per second if the disk is to roll without slipping? Okay, if it's going to roll without slipping, this roll without slipping statement right here means that omega is equal to, or r times omega is equal to v center of mass. All right. Now we're using the work and kinetic energy theorem. So how much work, that would be W, and we know that that should be equal to the change in kinetic energy. That's work kinetic energy theorem. We're given a mass, we're given a radius, we're told that it's a solid disk. What's important about a solid disk is you can look up the moment of inertia for a solid disk. It's 1/2 of mass times radius of the disk squared. So we're looking at a 1/2 mr squared for moment of inertia. Okay, so this means that my total work, W, should look like the final total kinetic energy minus the initial total kinetic energy, which from rest was 0. So this basically looks like 1/2 times, let's put it in terms of translation and rotation. So this would just be the translational final plus the rotational final. Okay, and I'm writing it like this because we might as well get how much of each of these two, rotational and translational, as part of our solution. So translational kinetic energy, that's 1/2 mv final squared. That's 1/2 of 2.0 kilograms times 4.0 meters per second squared. That is 16 joules. All right, what about the rotational part? The rotational kinetic energy is 1/2 I omega squared. That's 1/2 of mr squared times omega squared. Except for that we know that r squared omega squared can be regrouped. So this ends up looking like 1/4 of m. R omega is v, so we would have v squared. And that's just half of this number, and so that ends up being 8 joules. Notice that this is 1/2 of 1/2 mv squared, and I already have 1/2 mv squared here with 16, so I get 8. So my total work must be the sum of those two, which is 24 joules. All right, so that's it for today's video. Hopefully you learned something today, and as always, thanks for watching.